Okay, now we have an important two lectures today. These two lectures will talk about the design of digital filters. As you know, basically we have two kinds of digital filters. First one will be the FIR filter, and the second one will be the IIR filter. To understand what's going on, now let's go to the whiteboard to explain the classification of the filters. Then I'm going to talk about the design of FIR and the IIR filters. It's not working, I know. Well, first kind will be the FIR filter, and the second one will be the IIR filter. FIR and the IIR filters. I don't know why whiteboard is not connecting. Try again. Okay. Basically, we have FIR and IR filter kinds. To design FIR filter, we have to use three techniques, really. We have to design FIR filter, which are the window method, optimal method, and the frequency sampling method. Of course, as you know, we don't have enough of time, so I'm going to talk about the window method to design the FIR filter. And for the IR filter, we are going to talk about the pole zero placement method and the impulse invariant and the bilinear Z transformation. Now, when we talk about the design of an FIR filter or IR filter, what will be our objective is to determine the coefficients of the filter. I mean edge of n. Well, so whenever you are going to design any filter, our objective is what? Is to determine the coefficients of the required filter. We have some restrictions or some requirements we have to do. For example, basically, we look for linear phase FIR filter. Linear phase FIR filter. To design a filter, we have some requirements. For example, the phase requirement and the magnitude. As you know, in the magnitude, we have, for example, band pass filter. We have yeah. Okay. Yes, it's connected. Okay. Now, good. We said that we have two kinds of filters. Okay. FIR filter and the IIR filter. These are the digital filters. Digital filters. FIR filters, we are going to use what? We are going to use window method. Window method, optimal method, and finally we have bilinear Z transformation. To design IIR filter, we have another techniques. First one is called pole zero placement method. Second one will be impulse invariant method. invariant. And third one will be bilinear. Sorry, I did a mistake really here. Optimal method, and in the FIR, the other technique will be frequency sampling. Sorry, frequency sampling method. And here we have bilinear Z transform. So for every kind of the filters, the most popular techniques are 3x3. Okay, so Windows method, optimal method, frequency sampling, and for the IR filter, we have pole zero placement method, impulse invariant, and bilinear Z transformation. Of course, today in this lecture, we are going to talk about the design of the FIR filter using the window method. But before talking about the design of the window method, it requires what? Let us talk about the tolerance scheme of any filter, and then we will be able to understand the design requirement. So first of all, let us talk about the low pass filter. Generally, low pass filter will pass the signal which have what? Which have a frequency less than the cutoff frequency of the low pass filter. So let us first of all sketch or draw the magnitude spectrum of the low pass filter, but I'm talking about a practical low pass filter, not ideal low pass filter. Well, it's good. Now this will be F in hertz, and this will be edge of F. Now practical low pass filter will be as follows. Okay, now we have a region which is called a band pass filter. Then it will be followed by a transition region, and then we have the stop band region. Now these regions, this one is called what? This one is called pass band region. Okay, pass band region. This one will be stop band region, and in between, of course, we have another region. This region will be called what? Will be called transition region. Transition region. Okay, now, so we can what? We can distinguish the three different regions in the practical filter magnitude spectrum. Okay, this spectrum is called magnitude spectrum. So we have pass band region, stop band region, transition region. Now these points, okay, this point is called pass band edge frequency, FP. Okay, pass band edge frequency, FP. This point is called FS, stop band edge frequency. Okay, stop band edge frequency. And in between, in the midway between the FP and FS, we have what? We have the cutoff frequency FC. Okay, so this point will be stop band edge, stop band edge. Okay, this one will be pass band edge, pass band edge, and in between will be what? Will be cutoff frequency, cutoff frequency. Okay, now this is what? This is the tolerance scheme, and this scheme is very important to understand the requirement of any filter. Now, by now we have talked about the tolerance scheme of the low pass filter. Of course, we have, say, high pass filter, band pass filter, and band reject filter. Of course, we may have considered another type of the filter, which is all pass filter. Okay, when the signal or the filter or the electronic circuit passes all the signals, of course, practically it's very difficult to implement all pass filter signal. Well, Now, another important point in the design of the FIR filter is called the linear phase response. Okay, linear phase response.
سيدة
بله
بس our FC cut off چیه أول بني
هذا cut off frequency.
تمام سيدة
هذا cut off frequency. Cut off frequency. Now, linear phase response. Now, can anyone tell me what do you mean by linear phase response? شيء linear phase يعني. Can anyone tell me what do you mean by linear phase? Well, now, many times I have told you, whenever you hear about word linear means what? Means we have equation of straight line. Okay, word linear means what? Means we are talking about straight line equation, no more, no less. Well, now let us talk about the phase spectrum. Okay, phase spectrum. Now, in the previous diagram or figure, we talked about what? About magnitude spectrum. We said that magnitude of h of f. Okay, now we have another axis. Okay, in this time we are going to talk about what? About the linear phase. Okay, or the phase of the edge of f. Look, angle of edge of f. It means that what? It means that we are talking about phase spectrum, and this one will be what? Will be the f-axis. Okay, f-axis and the phase axis y. Now, what do you mean by linear phase? Look, please. The most important thing is the passband region. Okay, passband region. Of course, the region after the cutoff frequency, we are not going to talk about the region after the cutoff frequency. So, look, please. I'm going to highlight the cutoff region, for example. Okay, say this is the cutoff region, cutoff frequency, I mean. Now, the phase from 0 up to FC must be linear. Okay, we looking for what? Looking for phase to be linear in this region from 0 up to what? Up to FC. Why? This is the passband region. I mean, I'm going to pick up the signal which lies where? Inside the passband region. Of course, outside the passband region, I'm not going to take care about the phase of the filter after the cutoff frequency. So, for example, look at this example. Now, here we have linear phase. This is a linear phase, okay? But outside the passband region, we may have what? Nonlinear phase. So it's okay. We don't have any problem. Look, the equation here of the phase to be what? To be a straight line equation. Well, another kind of the phase spectrum to be linear, for example, this one. Again, this one is what? Is a linear phase. Well, or a straight line, I mean, y equal a constant. Okay. Again, this is another example for what? For linear phase response. Okay. So when we talk about linear phase, it means that what? It means that the phase spectrum of the filter within the pass band region will be what? Will be a straight line equation. This will be the definition of the linear phase response. Of course, if we are going to use FIR filter, at that time we can guarantee that the phase will be linear. One of the important features and characteristics of the FIR filter is what? Is that the filter characteristic will be linear. I mean, phase spectrum of the designed filter will be linear. Now let's go back to the slides, PowerPoint slides, and continue in the lecture. We said that all the three can lead to linear phase FIR filters. Now, to design an FIR filter, we have to find out at the beginning the ideal impulse response of the required filter. Now, in this method, use is made of the fact that the frequency response of the filter HD of omega and the corresponding impulse response HD of n are related by the inverse Fourier transformation. Now, you have h of omega, which is in frequency. Now you can what? You can determine inverse HD of omega to get what? HD of n. So based on the frequency response of the signal, we are going to determine the edge of n of the filter in time domain. Of course, using what? Using the inverse Fourier transformation equation. Now, the subscript D is used to distinguish between the ideal and the practical impulse responses. The need for this distinguish will soon become clear, for if we know HD of omega, we can obtain HD of n by evaluating the inverse Fourier transformation. We said that practically we don't have sudden changes. By now we are going to what? We are going to take an ideal low pass filter. Okay, ideal low pass filter, ideal high pass filter, ideal band pass filter, and ideal band reject filter to be taken, and we are going to perform the inverse Fourier transform for these different kinds of filters to get what? To get edge of n for what? For low pass, high pass, band pass, and band reject filter. As an illustration, suppose we wish to design a low pass filter. Now, we could start with the ideal low pass filter response shown in figure below. Okay, we said that we have ideal response and what? And the practical response. And I have talked about the practical response. In practical response, we can recognize the three regions: pass band, transition, and stop band region. Well, now we could start with ideal low pass response shown in figure below, where omega c is the cutoff frequency and the frequency scale is normalized t equal to 1 by letting the response go from minus omega c to omega c. We simplify the integration operation, thus the impulse response is given by. Look, please. Now, this will be the figure, okay, I'm talking about. Well, this will be the low pass filter. The low pass filter. Its cutoff frequency is band from 0 to omega c, and minus omega c to omega c will be what? Will be the double side spectrum. Of course, if you are going to draw single side spectrum, at that time it will be from 0 to omega c, but in most of the time we are talking about what? Double side spectrum for analytic operations. So the signal will be from, the filter will be arranged from minus omega c to omega c, and its magnitude equal to 1. As you can see, this will be what? HD of omega. Okay, this is HD of omega, as you can see. Now its inverse will be HD of n. HD of n. Now, before performing the integration and obtaining the result, look, please. You have studied the Fourier transformation in second year class, and you know, when we talk about the Fourier transformation of rect function, يعني AT rect FT, its Fourier transform will be what? Will be sinc function, okay? And here again we have what? We have a rect function, okay? This is what? A rect function. So the output will be what? Will be sinc function. Well, this is the sinc function. I mean, after performing the inverse Fourier transformation, it becomes what? Becomes sinc. We said that rect in time will be sinc in frequency. If you have a rect in frequency, it will be sinc in time due to what? Due to the duality property of the what? Of the Fourier transformation. Now, to perform the inverse Fourier transformation, we are going to follow this equation: HD of n 1 over 2 pi minus pi to pi. Okay, minus pi to pi. Of course, the signal limit will be 1 e to the j omega n d omega. Of course, when you talk about minus pi to pi in digital systems, it means just as talking about minus infinity to infinity. Now, 1 over 2 pi integration from minus omega c to omega c, e to the j omega n d omega n. Of course, after performing the integration and substituting the upper and lower limits of the integration, we get 2fc sine n omega c over n omega c when n not equal to 0. Okay, not equal to 0, and it will be 2fc when n equal to 0. Okay, this is a mistake in the book. Okay, this is when n not equal to 0, and 2fc when n equal to 0. Now, this is about the integration, and I mean the inverse Fourier transformation. So, of course, we are going to do the same thing for what? For the whole kinds of the filters. I mean low pass, band pass, high pass, band pass, and band stop filters. Look, please. Now, here we have a table. Okay, this table will be supplied in the final year exam. So when you are going to design a filter, say FIR filter, high pass, low pass, band stop, band reject, what are you going to do? First of all, you have to pick up the equation of the ideal impulse response. Well, ideal impulse response. Look, please. Now, for example, for the low pass filter, okay, for the low pass filter, what we have for the low pass filter, we have HD of n when n not equal to 0. Okay, HD of n when n not equal to 0, it will be 2fc sine n omega c over n omega c. So please look at this equation. This equation, we have only one missing parameter, which is what? Which is fc. So if you determine the fc correctly, then easily you can determine this equation. Well, after that, you are going to what? You are going to substitute the values of n in this equation. Of course, when n equal to 0, it will be 2fc. Look, please. It will be 2fc. When n not equal to 0, at that time, you can use this equation, n equal to 1, 2, 3, 4, 5, 6, 7, and so on. Well, so all we are going to do is what? Is to substitute the value of n. Well, for n equal to 0, n equal to 1, 2, 3, 4, 5, 6, and so on. Of course, some filters we have about 51 coefficients, 53 coefficients, 100 coefficients, 200 coefficients, and so on, based on the what? Based on the kind of the filter and the acceptable, say, tolerance in the design of the filter. Well, second kind will be the high pass filter. Look, there is a big similarity between the equation of high pass and low pass filter in the time domain. I mean the impulse responses. They are the same, except we have minus, and the HD of 0 for high pass filter will be 1 minus 2 FC. Then we have two equations for the band pass filter and band stop filter. As you know, when we talk about band pass filter, we have two cutoff frequencies, F low and F high, or F1 and F2. Okay, so the equation will be just as the combination between low pass and high pass filter to get what? To get band pass filter. Again, here we have a combination between band pass and high pass and low pass filter to what? To perform the required ideal impulse response. So first of all, when you are going to design any FIR filter using the window method, first thing what we are going to do is what? First thing we have to pick up the correct impulse response, ideal impulse response for the filter. Well, now, after selecting the correct kind of the impulse response, as we have said in the previous table, now we have another table. Look please at this table. This table consists of these columns. Okay, first column will contains the name of the window. Okay, name of the window. Second one contains what? The transition width. Third one will be the pass band ripple, a main loop, stop band attenuation, and finally we have what? We have window functions. Well, let us understand what's going on. First of all, the easiest one, let us talk about the stop band attenuation. Look, please. Stop band attenuation. Of course, when you are going to design any filter, we have what? We have some requirements. Say, the stop band attenuation. Sometimes, for example, when we design a filter, we say, for example, stop band attenuation must be greater than 50 dB. No less. Okay. So in this case, when you're talking about 50 dB, at that time, look at the stop band, which is supplied by the rectangular window. It's 21. It's less than 50. So this kind of window will not be adequate for the design of the filter, which has what? Which has stop band attenuation greater than 50 dB. Hanning window again is less than 50 dB. Again, this kind of filter will be what? Will be discarded or skipped. Finally, look at Hamming window. Hamming window has stop band attenuation, which is 53 dB. So in this case, we are going to what? We are going to take the Hamming window or Blackman window or Kaiser window. Well, based on what? Based on the stop band attenuation. So we have what? We have some conditions we have to follow to determine what? To determine the kind of the window, to select the suitable kind of window. We said that what? We said that based on the problem requirement. Good. Now, after selecting, say, the window type, uh, say it is Hamming window, let us go and pick up the equation of Hamming window. Okay, the equation of Hamming window. Now the equation of Hamming window will be 0.54 plus 0.46 cosine 2 pi n over what? Over n capital. Now, what is the missing parameter here? The missing parameter here will be what? Will be n capital. So we have to what? We have to determine the n capital. Of course, in this case, how we are going to determine the n capital? Okay, how we are going to determine the n capital? Of course, we have to go to the second column. Look, please. At the second column, we have what? We have this equation, which is 3.3 over n. And look at the title of this column will be what? A transition width. We said that we have 3 different regions in the filter. So this column, I mean 3.3 over n capital, represents what? Represents the transition width of the filter. So if you are going to equate this value, I mean 3.3 over n, by the transition width, at that time, we can what? We can calculate the n capital, okay? N capital represents what really? N capital represents the number of filter coefficients, okay? It will represent the number of filter coefficients. Of course, if you have determined the filter coefficients, say, to be 21, to be 5, 7, 11, 10, 20, 40, now we can what? We can directly substitute the value of n capital in this equation. So at the beginning, we have what? We have picked up the equation of ideal impulse response. In the second case, we are going to what? We are going to select the suitable window type and determine the n capital. Then the next step will be just substituting the values and calculating the coefficients of the desired filter. Of course, after that, we have what? We have the steps by which we can what? We can determine the filter, FIR filter coefficients using the window method. Now, specify the ideal or desired frequency response of the filter, HD of omega. Obtain the impulse response, HD of n, from the table, first table, as we have talked about, by using, of course, the inverse Fourier transformation. and the HD of n are summarized in the table. Select window function. Of course, how we are going to select the window function? Based on the what? Based on the requirements. Say we have sometimes stop band attenuation and pass band ripples again. Well, look please, these are the values for the what? For the pass band ripple. Now, sometimes we look for what? We look for low pass band ripple. Of course, what do you mean by pass band ripple? To understand what is meant by the the band pass ripple, let's go to the whiteboard again to understand what's going on. Now, we said that we have two important parameters: stop band attenuation and pass band ripple. Of course, we are looking for what? We're looking for flat pass band region. Flat pass band region, and if it's possible to obtain a flat pass band region, it will be better. Look, this will be this will be the axis of the filter. Well, now we have the following. Well, now this fluctuation, okay, this fluctuation is called what? It's called pass band ripple. Okay, these ripples are undesired, so we are looking for what? We are looking for such a filter really to be flat. Okay, flat. I mean, we are looking for pass band region, which is what? Which is flat without any ripples. Okay, it's better for us to get a region, pass band region, or flat pass band region is better. Now, again, what do we mean by stop band region? Stop band attenuation, really, the distance between the pass band region and the stop band region will be what? Will be the stop band attenuation. Of course, the gain inside the pass band region, the gain inside the pass band region will be 0 dB. Of course, what do you mean by 0 dB? What do you mean by 0 dB? What is meant by 0 dB?
It is we can't select that value from the table.
لا خير 0 دي بشي معناها 0 دي يعني تشتى 0 دي يعني تشتى
It means there is nothing.
لا خير شو nothing 0 دي بي تشتى قيمتي 0 دي بي ان ريشيو چنده قيمتي 0 دي بي ان ريشيو چنده
1
1
10 to power decibel over 10. Yeah, it's 1.
دقيقي okay, it's very good.
Just
يعني تشي 1 يعني تشي تشتى 1 بس بالي خوب الرجال جماعه قالك مهمه. The relationship between the V out and V in the pass band region, what? V out equals to V in. Okay? V out equals to V in the what? In the pass band region. Okay? Now, at cutoff frequency, which is what? Which is minus 3 dB point. Okay? Minus 3 dB point. Now the relation between V out and V in becomes V out equals to 0.707 V input. Oh, okay. So the relationship between output volt and input volts in the passband region, V out equals to Vn. And at the cutoff frequency, the relation becomes V out equals to 0.707 V input. Another one may ask me about what? About, say, the relationship between V out and V in the stop band region. Of course, it depends upon what? Upon, for example, the stop band attenuation in dB. Say we have 20 dB, we have 10 dB, we have 30 dB, and so on. So at that time in V out and the VN in the stop band region, we can what? We can expect that the VN is very small. Okay, how? Look, يعني for example, V out equals to مثلا 0.01 VN. Okay, it is attenuated. Okay, V out at stop band region will be about, for example, 0.01, 0.001, 0.001, and so on. Of course, don't forget that the passband region and transition region and stop band region, we are talking about what? About different frequencies. So the filter will attenuate and pass the signals selectively. يعني إن شاء الله selectively. يعني مثلا signals from say 1 kilo, or for example from 0 to 10 kilo will be passed. The signals after 10 kilo will be rejected. Okay, so the filter selectively, okay, working on the signals. Okay, this is meant by the passband region and the cutoff frequency and the stop band region. So when we talk about stop band region or stop band attenuation, we are looking to what? To attenuate the signal which has frequencies greater than the cutoff frequency. And the relationship between the V out and VN in the passband region will be V out equals to VN. At cutoff frequency, V out equals to 0.707 V input. Now, let's go back to the slides and to continue the lecture. Now, we have mentioned and talked about the stop band attenuation, passband ripple. It's not important. I will talk about the main loop and the side loops. Okay, and we have the transition region. From the transition region column, we can determine the number of filter coefficients. Well, specification and then determine the number of filter coefficients using the appropriate relationship between the filter length and the transition width, delta F, expressed as a fraction of the sampling frequency. Now we have the final step: obtain the values of omega n for the chosen window function and the values of the actual FIR coefficient h of n. Look, please, h of n will be what? Will be multiplication between hd of n and w of n. Okay, we said that based on the filter type, we are going to what? We are going to select the impulse response of the filter. And based on again, the requirement of the filter, I mean amount of attenuation and the passband ripple, we can what? We can select the suitable window type. So in this way we can what? We can design the filter using what? Using the window method. Now look please at the incoming example. Here we have an example. This example can be used to solve and to use the two tables. Okay, the table of the impulse responses and the table of the windows. Look please at this example. We are going to talk about the full solution of this example. Obtain the coefficients of an FIR filter, FIR low pass filter, to meet the specifications given below using the window method. First of all, passband edge frequency, okay, passband edge frequency is equal to 1.5 kilohertz. Example, so FP is given by 1.5 kilohertz. Now, transition width is equal to 0.5 kilo. Okay, TR is equal to 0.5 kilohertz. And the stop band attenuation must be greater than 50 dB, and the sampling frequency will be 8 kilohertz. Okay, these are the requirements of this example or this problem. Now we are given these information, and what we are going to do, we are going to select the suitable filter coefficients. Look please at the table. Of course, now from the table, look, first of all, based on the stop band attenuation, we can select the window type. Okay, window type. So go back to the table, look for the stop band attenuation. Which kind of window has stop band attenuation greater than 50? Of course, the Hamming window and the Blackman window and Kaisar window. Now, my question is, my question is, now we have 3 windows will obey the requirement of the filter. But which one is the suitable one? I mean, are you going to prefer the Hamming or Blackman or Kaisar window? Of course, Kaisar window, I'm not going to talk about the Kaisar window in this course. Why? This requires the Bessel function tables. And as I think you are not familiar with the Bessel functions, so I'm going to talk about only Hamming and Blackman, Hamming and rectangle for the first 4 kinds of windows. Well, no problem. Now, which kind of window do you prefer? Hamming or Blackman? Which one is the better?
We should choose another parameter to choose that.
Huh?
We should bring another parameter to choose the right one.
No. Based on the
Why?
stop band attenuation, you can select. We said that we have what we need. We need 50 dB, must be greater than 50 dB. Now, the Hamming is 53 and the Blackman is 74 dB. Now my question is, which one do you prefer? Which one do you prefer?
In my
Blackman.
Harming baştıra da niziki penci anna.
Buchi?
Niziki penci ama ona ma penci divid vet. A penci sepçe ki بترا.
لا طبعا بنذكره وبينجي بس نا طبعا قال حفتي وشار وهشته باشتره طبعا يعني چند اتنيويشن زاده چند باشتره طبعا ابا شرطك دي بجمته بس نوكا بري خوبدن كولوم رقم 2 رجاء بري خوبدن كولوم رقم 2 وكي من قوتته الترانزيشن ويدث ابا ثابته ترانزيشن ويدث يعني قيمتي ترانزيشن ويدث ثابت اوكي the value of the transition width is constant. So when you are going to equate a constant by, for example, 3.3 over n and 5.5 over n, we said that n will represent what? The number of filter coefficients. So Hamming window will be what? Will lead to less number of coefficients, while the Blackman window will lead to what? Higher number of coefficients as compared with Hamming. Of course, increasing the number of filter coefficients will lead to what? Needs more processing time, and the system will be what? More complicated. So always we are looking for what? To meet the requirement of the filter with what? A plus looking for what? Looking for decreasing the computation and complexity of the system. Of course, now let us take a rest for 10 minutes and we'll go back to continue the lecture. Okay?
Yes, Seyda. Tiyarak Seyda. Seydosh lecture page ويفا تا ناكينات upload ناكينات سويت دا كزحمنا بدي شيفر كي كده دا.
lecture كان بين من همي lecture من upload كسري موقعي.
Seyda منك يقف كي ساكرية تدانين نزابو شيء.
كيش lecture؟
موديل دا.
كيش lecture؟
شش وحفت ويتويفا عبيش بينجو ويفا خوي تدانين.
درست تحكي سري موقعي خر كامل من ابلود كرد حتى سحكت زان شيء ويك 1 ويك 2 يعني بيشتغل مستعمل كتن ويك 6 حاف نه ده 11 12 درست
سيدا ويك بس اودي بي دي اف اودي ليكتشر بخو
ايه
سيدا تدانينا مش سحكري
باوربوينت ليكتشر بخو تدانينا
باوربوينت شنينا
باوربوينت ليكتشر سيدا
مالات باوربوينت من همي ليكتشر من اوديك الابلود كد هاش سحكي اودي موديل نينا هي زيب فايل كده زيب فايل نينا تايك زيب فايل كده زيب فايل كي اكستراكت خلاص همي محاضره تدايه تقريبا 16 فيديو 16 باوربوينت تدايه
درس سباس
عزيزي مسر شافا زانشا بس عرفتك دي ور بقرم 10 دقائق وفاشن دي جارك دي دسبك ان شاء الله يلا